But really, on top of, and that was just, kind of one section with the nuclear equations. There's other things that I'm pretty much going to discuss for this chapter. And I'll be honest, one of the things that I'm really going to have you focus on is the half-life type things. That concept to me personally, I find it really important because we're somewhat rushed with time. The radiation measurements, I'm not going to expect you to do calculations with those, and you'll even see with the homework assignment, I don't. But the half-life, they're kind of simple, so we will go over that in a little bit greater of a detail. But I do want to still cover the radiation measurement and obviously the applications of radioisotopes as well. So how do we measure radiation? I don't know if anyone's ever seen a Geiger counter, or they do them a lot in movies where they have the little clicks, the little pops, and every time it pops, it's basically reading radiation, and that pop is basically the meter basically having a voltage reading. And the reason that is typically what happens with the radiation. When the radiation is emitted from a radioactive source, it collides with particles in the air. And when it collides with the particles in the air, it pops off the valence electrons for these particles in the air. And when it runs into the particles and strips off an electron, now I have an electron, which is a charged particle. And from the molecule or the air particle that I strip the electron, I have a positive charge. And we've discussed with electrolytes that we need ions, charged particles, to conduct electricity. So when you're reading a radioactive source with a Geiger counter and you're hovering over it, all of a sudden this radiation's knocking off all these electrons from gas particles. So above the radioactive source, you have these electrons that are negatively charged and these particles that have been stripped of electrons with positive charges because the emissions from the unstable nucleus has stripped them. And then the detector actually reads those electrical charges and converts it to an electrical signal, which is basically converting it to a voltage. And the Geiger counter reads it and makes a clicking noise. So that's why in the movies, when you ever see like movies, if the Geiger counter goes over something, at first it might just click once, but then when it's supposedly over something harmful, you hear a lot of clicks. Well, that's because it's emitting a lot of radiation and it's stripping a lot of particles of their electrons. You can think of that as making a bunch of free radicals. Because essentially free radicals are just unpaired electrons. So if I knock off one electron, now I have an unpaired electron. That's a free radical. So the units that you can use for radiation is, the Curie, and it's the number of atoms that decay in a second. It's a really common one. The rads, this is one that's really common too, especially with Geiger counters, is the radiation absorbed dose, so the measures of radiation that absorb by the tissue, and the REM. And the REM is basically, hello? Okay. And the REM is basically a radiation equivalent to the damage caused by different sources. So these are very common ways to measure. And if I remember, I think it actually is the rads for the Geiger counters. I might be wrong with that. I haven't used one of those in a while. So with the different ways of measuring, with the Curies, the rads, and the REMs, you have different units. And this is where I'm going to tell all students currently is I'm not going to really be very critical with these types of units. We don't have a lot of time to do all these calculations. So this is kind of one area where I'll be honest, I probably won't have this on the final, just to give you a heads up, just because it's kind of last minute, and I'm not going to emphasize a lot of these different calculations to you last minute. But I just wanted to talk about it. So typically with the Curie, we're measuring the activity of the actual radiation. The rads are the absorbed dose, and the rem is the biological damage. Can you guys hear me? Because my computer is kind of acting weird. It's freezing up here and there.
Yes, I can hear you.
Okay, okay, good. So a lot of times if you work in a lab, they do the REM, and I don't know if anyone's ever had a little, those radiation badges, right? Like if you work in a hospital, sometimes they have you wear radiation badges, and those are actually, I think that's absorbed dose. It measures how much radiation that individual is absorbing per day. So if you ever work in like labs that deal with radioactive substances, or if you work in a hospital where they might use some radiation for medical purposes, you might wear a little badge, and every month they'll check the badge to measure your absorbed dose. What people have to realize is, you know, just like electromagnetic radiation, radiation gets kind of a bad rap, and sometimes they're really scared, but believe it or not, you know, there's a lot of natural occurring radioisotopes, and they have, you know, purposes. So for medical and dental procedures, we use them. The key is we want to minimize our exposures to it, and we want to increase our distance. So if there is a radioactive source, you want to increase your distance. That is just what you want to do. But you do get radiation. There's natural forms. I mean, we get it from the ground. In air, there's radiation. I mean, there's gamma rays, there's UV rays, right? There's radiation in the air, right? Cosmic rays. Cosmic rays basically means from, you know, the solar, from the universe, right? Coming from the sun. And then there's forms of radiation, you know, medically. You know, now depending on, you know, whether it's going through organs, we start seeing that the radiation is a larger dose, right? So if you start testing organs now, like if you do some type of gastrointestinal x-ray, that's a whole biological system. Now your dose is a lot larger than if I'm just getting an x-ray, because I'm going through a whole system. So your doses are larger. And just like TV, right? Electromagnetic radiation, TVs emit some radiation as well. Okay. Actually, before I move on, does that make sense? So again, with I'm sorry, I cut people off. What was that? I'm sorry.
No, I was just saying yes, it makes sense.
Okay. So the key is you want to protect yourself with protective clothing if you're ever interacting with radiation. And the other thing is you want to make sure that you increase your distance. I always tell students, and I think I say this on the first day, is, you know, if working in a lab if you're pregnant and you're concerned about working in a lab, let me know. And I always let students know, if you're pregnant, let me know, because if there is some source of radiation that's a high source of an emitter, then we want to make sure to protect you, because fetuses, their cells are undergoing mitosis at a much faster rate. So they absorb, because they're more active, they absorb the radiation a lot faster, and it has a larger effect on people, right? So just make sure that if you work in a lab and you have a concern, you bring it up to your instructors so that they can let you know if they have some high dose emitters. I mean, for our class, we didn't really deal with a lot of radiation, so we were fine. The topic that I do think is pretty simple, and it's useful, especially if you go on to biology courses as well, as kind of half-life decay. And a lot of times you'll see the half-life written out as like a t to the 1/2. And what that basically means for half-life, it's the time, right, for whatever sample you have, for half of it to remain. So basically a half-life is the amount of time that it takes half of the radioisotope to change and decay. Okay, so here's a sample, right, of a radioactive isotope. It's iodine 131, okay? And I originally have 20 grams. After one half-life, what that means is I have half of 20 grams. So after a half-life, I only have 10 grams. After another half-life, so whatever time period that is, let's say it's 8 hours. So the first 8 hours, I would go from 20 grams to 10. And then from the next 8 hours, I would have another half. So half of 10 is 5. And then another half-life, I would have half of 5, which is 2.5. So after every half-life, I have half the original amount of that isotope. Okay? So someone might be asking, well, what's it changing into? Well, it's going from, you know, just like in our chemical equations or nuclear equations, it's going from one isotope to another. So here's a little test. What type of radiation based on this changing of isotope did this undergo? What type of decay? What kind of change? So was it a alpha, a beta, a positron? So going from this iodine, right?
Was it a beta?
Yeah, it was a beta. Good.
Okay.
Why was it a beta? Excellent. It was a beta.
The atomic number changed from 54 to 53.
Or from 53 to 54.
Oh, sorry, yeah. 53 to 54.
So increased by 1.
Yes. So the mass number stayed the same, but I went up in atomic number. Why? Remember, with the beta decay, right? The neutron changes to what? A proton and shoots out an electron. So we see an increase in the number of protons, but the mass is the same because neutrons and protons are the same. And we could actually even calculate that, right? So 131 minus 53, what is that? So, yes, so I have over here 78 neutrons and 53 protons. And over here, one neutron changed to a proton, so what do I end up getting? 77 neutrons, but 54 protons. And you don't have to do that, but I'm just showing you. You can just look at what you guys did. Saw that the mass number stayed the same and that the atomic number went up 1, so that was a beta. Good, that's excellent, good job. And even though we weren't doing nuclear equations, I want to show you that you could figure one out on the fly. The big reason I'm showing this is, you know, with your first half-life, you get half of the sample. And then in your next half-life, whatever amount of time that is, you'll get half of what remains there. And then in your next half-life, you'll get half of what remains there. Now, why is this important? It's an exponential, right, decay, right? So you learn this in mathematics, and you learn this in biology, that it's an exponential decay. And what that means, right, is there's an asymptote. And the asymptote is you will never have 0. You could always have less. So you'll never have 0. And that's like hard for people to understand, right? Right. So if I have 2.5 grams, I could still have half of that, 1.25. I could still have half of that, right? And I mean, you could have half of 0.000001 grams. So with an exponential decay curve, there's an asymptote. You will never have just 0. And that's kind of mathematically when math gets kind of cool, when you have like these asymptotes and limits and things like that. And you see it in science all the time. So the decay curve shows this, it's not linear, right? And we see that, I guess it wasn't 8 hours, it was 8 days. So after 8 days, I have half of the material, 10 grams. Another 8 days, so 16 days is 2 half-lives. Now, 2 half-lives, I went from 20 to 10, and then from 10 to 5. And then another half-life, I went to 2.5, and I can keep going, keep going, keep going. So the reason why I like bringing up half-lives is there's radioisotopes everywhere, and they're naturally decaying. And some have really long half-lives, and some have really short half-lives. So the ones that have really short half-lives are extremely useful in the medical field, right? So if you want to see if you have a overactive thyroid, they sometimes make you drink a little cocktail, and that cocktail has radioisotopes in them. And the way the overactive thyroid absorbs those radioisotopes is it's going to absorb it quickly than a normal functioning thyroid. So you can take images, right? You can do images of this absorption of the thyroid of the radioisotope and get a lot of information on it. So what you don't want to do is have to wait a long period of time to get this imaging. So in the medical field, your radioisotopes that you use, well, they have to be practical. So you notice that the isotopes in the medical field, their half-lives are only for days, so D stands for days, or a couple of hours. That way, you can do scans, and after the person ingests the radioactive isotope, it gets out of their system quickly, okay? So there's a lot that are used in the medical field for observing organs and how they are functioning. Now, the other useful ones are the ones that are naturally occurring in nature, and they tend to have much longer isotopes, okay? Or half-lives rather, sorry. And the Y stands for years. So you may have heard of carbon dating, right? Carbon dating, right, is where you have the carbon-14 undergoing a beta decay and changing to carbon or nitrogen. Well, sorry, thinking ahead of my, before I write it. It converts to nitrogen, right? But the half-life is extremely long. It's 5,730 years. So carbon dating is really useful for dating things since, like, artifacts of human civilizations, right? So if I want to, some will argue we've been around for hundreds of thousands of years, but civilization, maybe 10,000, maybe 15, 20,000 years. So if I'm finding a scroll, right, an ancient scroll that was written on paper, which has carbon, and I can compare the abundance of this carbon-14 to the nitrogen-14, I can determine how many half-lives have occurred based on those ratios of percentages. So it's really useful, carbon dating, for dating things that, because the half-life is 5,000 years, for a couple thousand years, right? Well, why does it take so long for it to decay? It's a pretty stable isotope. I mean, they have longer decays because they're pretty stable. Now, some of these isotopes have extremely long half-lives, 4.5 billion years, right? Or 1.3 billion years. Why is that useful? Well, if I want to know how old the Earth is, right? If I want to know how old the Earth is, I don't want to look at something that has a half-life that's short. I want something that has a relatively long half-life. So these half-lives are excellent because they're really long. So with half-life calculations, right, it's pretty simple, all right? If I have 40 milligrams initially, after one half-life, right, I'm going to have 20 because I'm going to have half the original amount. There's another half-life. So there's 2 half-lives. I'm going to have 10. So essentially, you're having it for every half-life. Another way of thinking about it is, you could look at it as, you take, to figure out the amount that remains, you take the initial amount, which is the principal, you multiply it by 1/2, and you do it to the power of n. And the power of n is the number of half-lives. So if you have 2 half-lives, right, and I'll put in 40, instead of going 1/2 times 1/2, you do it to the second power, right? What's 1/2 to the second power? 1/4. What's 1/4 of 40? 10. So that's how you can do it. And if you don't like using this, notation of exponential notation, don't worry about it. Just say, all right, I started with 40, half of 40 is 20. Half of 20 is 10. If I had a third half of 10, it would be 5. So here's a question for iodine 123 isotope, which is used in the medical field, right? And how can I recognize that? It has a really short half-life, 13 hours. Extremely, practical. So if I have 64 milligrams, right, and it has a half-life of 13 hours, right, how much is left after 26 hours? Anybody want to take a guess, or?
16 milligrams.
Yes. Okay, so how can we do that? We can do it the way we did before. We could say, all right, we started 64 milligrams, right? And each half-life is 13 hours, and there's 26 hours. So 26 hours total divided by 13 hours, because so this is my time, and this is my time, my half-life, right? So if I divide those two, there's a total of 2 half-lives. So the first half-life, half of 64 is 32. The second half-life, the half of 32 is 16. Another way you could do this, and you don't have to do it this way, is 64, right? And then the 1/2 to the number of half-lives. If you're not sure how many half-lives, and see, when you go further in chem, it's not going to always be these fixed integers of 2. So a good way to do it is just write however much time, 26 hours divided by the half-life. So we would see that it's 64 times 1/2 to the second, which is 64 to the 1/4, and 1/4 of that is 16. But if this was like a 2.5, right? Let's say it was out of 35 hours, that's not a perfect integer. By doing it this way, we can still use our calculators. But for this class, we don't have to do that. I just like teaching it. If you move on to the future, you've at least somewhat seen this form and you're comfortable with it. Are there any questions with that?
No.
Okay, and you guys do not have to use this exponential form that I'm showing you. I like to give a little extra. This is totally fine. And it's fast, super fast. It's just, as you move forward, you're not going to always have perfect integers, so it's easier to do that.